This lesson is for FST, lesson 7.5 on complex numbers. Hopefully students know that when you do the square root of a negative number, that typically the graphing calculator will, or even a scientific, will tell you that that is an error, that you can't do it, you'll get a non-real solution. The reason is because we have developed an alternate way to handle this type of question by breaking it up into the square root of 16 and the square root of -1 instead. So we break off the negative, which is the part that's problematic, and we deal with the part that we can do in regular fashion. So the square root of 16 we know to be positive and -4. The square root of -1 has been decided or determined to be called an imaginary number. So we're going to call, anytime we have the square root of a negative, the letter I. And so now that problem can be written like it has a variable instead of saying it has no solution. So it's a way of helping us get around situations that we would normally get stuck in. We're allowed to continue to simplify. We just say then we get an imaginary number. Keep in mind that when you're working with square roots, it's important that you rewrite them in terms of I before you perform any other operations. So in a lot of situations, students would take the square roots here and combine them and say -16 times -4, but that would be dealing with the multiplication prior to dealing with the i's. So keep in mind, students, that you want to deal with the I part first and then simplify. So we know that the first part's going to make positive and -4i. The second one, hopefully you know, is going to make positive and -2i, because the square root of 4 is 2. The -1 is going to turn into an I. Those are being multiplied together, so now we'll say 4 times 2 is 8. I times I is I squared. The other thing about imaginary numbers students need to have memorized is simply that I squared is equal to -1. So if I squared is -1, then this problem is going to eventually substitute down into -8. So we started with a problem that could have potentially had a non-real answer, but because we used imaginary numbers along the way to simplify, we're able to come up with a number that's a real number answer. Our main focus today, however, is going to be complex numbers. Complex numbers have a real part at the beginning, meaning a real number to start, and then the second part of the complex number has an imaginary part, meaning it has an imaginary number in it. All complex numbers need to be written in that format, even if that requires you to rearrange. So on the first one, 2 plus 3i, that one's already in complex number form. The one below it, however, is not. The real part needs to be first. In order for us to change the position of the numbers, we would need to change to addition first. If you change to addition, you have to add the opposite. And now I can use the commutative property to flip-flop these and say 2 negative plus 3i. Now it's considered a true complex number. If you just have an imaginary number, know that that could still be considered a complex number because the real part is simply a 0. If you are working with a real number, know that you could turn it into a complex number as needed by including the presence of a 0i. Our focus today with complex numbers is doing the operations on them. Typical math operations here are addition, subtraction, multiplication, and division. Our focus today is going to be on addition, multiplication, and division. Pretty much the method that you'd use for subtraction is going to be almost the same as for addition. You're just going to subtract instead of add. When we're working with the first example here, notice the presence of the plus sign. The parentheses here are just to distinguish one complex number from another. But technically here we don't even need the parentheses. The parentheses are not indicating that we're multiplying here, they're just simply separating that one from that one. So all you would do here is add like terms. You would use the commutative property here to flip-flop the 2 and the 3i. So the 2 and the 4 get added together, and the 3i and the 2i get added together. So the real parts go with other real parts, the imaginary parts go with other imaginary parts, and you simply add. So 2 plus 4 there is going to be the 6, and the 3i plus 2i is going to be 5i. We handle it just like we normally would any other type of variable. Now when it switches to multiplication, meaning no plus sign in between, we would do regular FOIL here. So when you do FOIL, you do the firsts, outsides, insides, and lasts. When you get the lasts here, it's 3i times 2i is 6i squared. Keep in mind that 6i squared is really negative 6, because I squared is negative 1, negative 1 times 6 is negative 6. So the 8 and the negative 6 there are going to be like terms, those are going to be combined. And the numbers in the middle here, the 4i and the 12i, those are also like terms, so those would be combined to make 16i in the middle. So when we're all done here, the 8 minus the 6 is going to be a 2, and then the 16i on the end. Now that's in complex number form. So that's addition and multiplication. I'd like students to try a multiplication question on your own. Try it by doing FOIL, similar to what we just did. Pause the video and the answer will be displayed shortly. So hopefully you got negative 2 plus 14i. If you're struggling with FOIL, make sure you talk to me during class and I can help tutor you individually. Next up, we need to talk about complex conjugates. Sounds more complicated than it is. When you're working with a complex number and you need to know its complex conjugate, the numbers stay the same, but the sign in between them will go to its opposite. So a minus bi is the complex conjugate of a plus bi, and vice versa. So if you're working with 3 plus 2i as your complex number, its complex conjugate is 3 minus 2i. Just like on our second example, 4 minus 3i, its complex conjugate is 4 plus 3i. The reason that we need those is because of the next theorem. The complex conjugate multiplication theorem reveals that when you do a complex number multiplied by its conjugate, notice that there's no i's left in this problem. When you do a times a, you get a squared. When you do the o and the I of FOIL here, you're going to get negative abi and positive abi. Those are opposites of each other, so those are going to cancel. Then when you do the L of FOIL, you're going to get bi times negative bi. That's going to be negative b squared I squared. I squared, remember, is negative 1, so that's going to make that b squared go back to positive. So notice how in our answers there's no i's. The i's go away when you multiply a complex number by its conjugate. So that'll be beneficial to us when we do the next problem together. The book also gets into the relationship among the different sets of numbers, and so this graphic helps you organize your thinking there. It also starts to begin talking about how if complex numbers are introduced, now there's another set of polynomials that we are able to factor. Normally we can't factor x squared plus 36. We would only be able to factor it if there was a minus in between. But because of the presence of complex numbers like I, now we could factor that similar to what we would do in an x squared minus perfect square number situation. So when we do x squared minus 9, we can factor that as 3x minus 3, and that would work no matter what domain you choose, integers, real numbers, or complex numbers. If you do x squared plus 36, you would do x plus and minus 6. But because we need a plus sign in between, we have to introduce an I in order to get that to work out. So now that complex numbers are able to be factored, know that that opens up the possibility of you factoring x squared plus a perfect squared. Our last topic for today is dealing with imaginary numbers on the bottom of a fraction. When you see that happening, that I cannot stay in the denominator of the fraction, so you have to use a conjugate to get rid of it. The conjugate of the bottom is what you use, so in this case the conjugate of 5 plus I, which is 5 minus I. Make sure you multiply that on the top and the bottom. The top and the bottom need to be the same in order for this to work. Now let's go ahead and do FOIL on the top and the bottom. When I do FOIL on the top, I'm going to get 20 minus 4i minus 15i plus 3i squared. Now let's go the next step on that. I did negative 3i times negative I. Negative times negative is positive. 3 times 1 is 3. I times I is I squared. But I squared we know is negative 1. So that's really going to turn into negative 3. On the bottom, I'm going to do just the F and the L of FOIL because the O and the I are going to be opposites of each other. 5 times 5 is 25. I times negative I is negative I squared. But I squared is negative 1, so negative I squared is going to be positive 1. So my final answer now is going to be 17 for 20 minus 3, minus 19i for negative 4i minus 15i, over 26. I'm fine with students leaving their answer like that on a test or a quiz. Know that in the book, they're going to insist that you separate it into complex number form, which means you separate the real part from the imaginary part. One final comment here on this one before we finish for the day. Let's pretend for a moment that this was 18 over 26 and 20i over 26. If that were the case, you'd want to make sure to reduce both of those. So the 18 over 26 could both be cut in half because they're both even, so you'd get 9/13. And the 20 over 26, same thing. Those could both be cut in half, so you'd get 10i over 13. So just watch out for that, students. If you see numbers that can be reduced in this situation, you'd want to go ahead and reduce to lowest terms. We didn't have that on this one, so we can go ahead and just leave it as is.